Hi, I was so hoping to be here in person again, but my daughter lives upstairs and is having a baby next week, so we were really worried about COVID, and so I have to do this virtually. All over Europe, countries are trying to cut back on energy consumption and turning out the lights as a consequence of war. We've seen this movie before. Being a grandpa means that I'm old enough to remember the last time we had an energy crisis caused by war. I was in architecture school at the time. When OPEC cut off the oil to the countries that supported Israel, we were all talking about energy conservation for the first time. It had never been an issue before. Gas was rationed, people were lining up for hours for a little bit of gas. And Jimmy Carter told everyone to put on a sweater and turn down the thermostat, just like Emmanuel Macron is doing now. They were both trying to reduce demand for fossil fuels and electricity. They were driving at a crawl, probably cost Jimmy Carter the election. Everybody hated it, but he dropped the speed limits. This was an era when we were first thinking about super insulation, and this house in Saskatchewan in 1974 became an inspiration for Passive House. In some places, it was the beginning of the bicycle revolution. Not in the United States, where they basically started tightening car regulations and car fuel consumption, beginning of tighter building codes and reducing demand for fuel. Then supply-sider Ronald Reagan came along, smiled, cut a deal with the Saudis, and everybody started pumping again, and life was fine. Fracking made the energy problem better, but it made the carbon problem worse. Energy conservation and efficiency became a hard sell when you had all kinds of new sources of gas, from the oil sands to the North Sea to deep sea drilling to Alaska pipelines. It was all about supply. And we kept burning more gas and oil, and the temperature kept rising. Solving the energy problem didn't do anything for the carbon problem. Global warming was common knowledge and accepted, but everybody was having such a good time burning all that oil and gas and didn't take it very seriously. And of course, it was all very political. The Paris Agreement, after years of talk, finally set some limits on carbon emissions with a schedule, a carbon budget, and a target, a limit on warming to avoid catastrophe. According to the IPCC in 2015, they wanted to keep the temperature rise to 2 degrees. But in 2018, they figured that 2 degrees might be catastrophic, and there was an addendum to say below 1.5 degrees. And there's no ramp in reductions here. It's really a cliff. When this graph was done, the total remaining budget was only 420 gigatons. And with all the talk and all the agreements and everything else, the temperature kept rising, except for that little dip in the pandemic, and it's now rising again. And some have already given up altogether and have basically said we can't be saved, 1.5 degrees is out of reach. Others don't. Last April, there was the third climate change report, the third section, I should say, that basically said what we have to do to mitigate climate change. And nobody paid attention to this. This thing dropped like a brick. You got things like this. Earth on track to be unlivable. Story on page 3. Didn't even make the front pages. But the content of it was in fact extremely positive. As you can see here, the unit costs of renewables and batteries have dropped and their use has dramatically increased. Renewables for 2021 dominate the additions to power. And the IPCC report set out the fact that we could make changes, demand-sized changes, to reduce our carbon emissions significantly in industry, in transportation, and buildings. They went so far as to say that demand-side mitigation, changes in infrastructure, technology, and behavior could reduce global greenhouse gas emissions by 40 to 70% by 2050. As Amy Westervelt, a journalist, wrote it, the report made one thing abundantly clear. The technologies and the policies necessary to adequately address climate change exist, and the only real obstacles are politics and fossil fuel interests. So everybody keeps showing these graphs. We have to drop by the graph, these slopes of changes that have to be made. But in fact, it's much simpler than that. There's a ceiling, a budget, a number that they determined through their calculations that with what percentage do we have to stay under a certain temperature. So from 1850 until now, we've added 2,390 gigatons of CO2, and this is what we have left to stay under 1.5 at a 50% chance, 500 for 2 degrees, 1350. If we want bigger chances, it's a smaller number. And here we are again. The last time the tanks were rolling through the desert, now they're rolling through the streets of Ukraine. And we've got a gas crisis. They spent all this money to build this big pipe from Russia to Germany, and then they blew it up. So now we're in a situation that you can't get gas to Europe from Russia very easily, which has immediately caused huge problems of inflation in the UK, problems of supply that Germany is approving limits on heating and turning out the lights at night. And Portugal's inflation was the fastest rise in 30 years. Many people worry that the carbon emissions will spike even higher because countries like Germany are digging more coal and opening the coal plants, and Britain is looking at fracking, and liquefied natural gas is being shipped in, and it has a much higher carbon footprint than regular natural gas simply because of the refrigeration and the transport. Other people think that what will happen is another thing that happened in 1974. As Michael Liebrecht says, we're going to have the great clean energy acceleration. From now on, all three elements of the energy trilemma, security, affordability, and sustainability, are pushing in the same direction. The great energy price spike is going to give way to the great clean energy acceleration. Fatih Birol, the head of the International Energy Agency, says the same thing. After winter comes spring, the oil shocks of the 1970s resulted in major progress in energy efficiency, nuclear power, solar, and wind. Today's crisis can have a similar impact and help speed up the shift to a cleaner and more secure energy future. And energy efficiency is, of course, the key point in the Passivhaus concept that we're all here about. And the Passivhaus people make it very clear. Energy efficiency is the first renewable energy. So suddenly, we've got an issue of possible gas shortages in Britain and possible electricity power cuts and rationing. But people who live in Passivhaus don't have to worry about this very much because their houses act like a thermal battery. So as you can see here, when it's really cold, the temperature inside stays pretty constant for days and days and days. And in California in 2014, going the other direction where the temperature was getting up to 32 degrees Celsius, the temperature inside stayed cooler. They also have that ventilation system, the filtered ventilation system, that basically brings in fresh air and doesn't recirculate air. And this is very good, as they found in California in fires. When you have smoke and PM 2.5 in quantities, basically it can be filtered out. And that's why they're talking about Passivhaus being a good way to deal with wildfire smoke and indoor air quality. Even for COVID, This is really helpful. You don't want to recirculate air. We've never really talked about air in the way we do as water, but this doctor in Toronto has this great phrase, air is the new poop, that basically we have to start thinking about air, designing for air, engineering for air the way we do with water, and we've been doing with water for 100 years. So we know that Passive House will give you a healthy environment, enhanced control, wellness, elimination of toxins, of course, energy efficiency, and resilience. However, a very important consideration, and the key of this presentation, is that energy efficiency is not enough. Yamina Saheb is an energy analyst and a lead author in the IPCC report that I was quoting earlier, who put together what she calls the SER framework, the SER framework for efficiency, sufficiency, and renewables, and writes, the collective failure in significantly curbing emissions from buildings raises questions about whether the present approach to climate change mitigation policies is adequate and effective. Efficiency improvements combined with the slow adaptation of renewable energy and minor behavioral changes are insufficient to deliver. Now, renewables is something that you've been dealing with here in Portugal and installed your 57% renewable and installed more solar PV in the first half of 2022 than all of 2021. But renewables are a pretty straightforward issue. But let's look at sufficiency. This is my passion. I've talked about this before here, and I'm going to talk about it again just to remind you what it is. And I think the best example of sufficiency is figuring out what is the most appropriate way to do something with the least amount of material and resources. So, for instance, 100 years ago, everybody used a clothesline because that's all there was. So even the tenements of New York, everywhere, the clotheslines were hanging out. Then they invented the electric dryer, and in the 50s in the United States, the clotheslines disappeared and they all got electric dryers. But electric dryers have a real problem. They're like heating toaster coils and fans that just take air out of the house and throw it outside. They're expensive to operate just from the electricity and also for replacing all the air that they throw out the back of the house. So they invented this very fancy, expensive heat pump dryer that uses heat pump technology to be recirculating everything around the dryer inside, so it doesn't even have an outside vent. And they're complicated and they cost 3 times as much money. But what do you do in Portugal that works perfectly well because you've got the climate for it? I took pictures of this all over Lisbon. People hang out their clothes to dry. And they do this all over China and everywhere else too, and actually believe that the clothes smell better and feel better than they do getting torn apart in an electric dryer. The key message is efficiency is great, but efficiency without sufficiency is lost. It basically gets buried. Everybody knows we could produce and consume more efficiently than we do, but the problem is efficiency without sufficiency is lost. This is written by Samuel Alexander, an Australian expert on this. Despite decades of extraordinary technological advancement and huge efficiency improvements, we keep using more energy. Demand keeps increasing. There's another thing also that's called Jevons paradox. You know, in the 70s, when there was the oil crisis that we've talked about, all the car manufacturers started developing small cars, like the Pinto in the States, a terrible car, but they were responding to the market. My mom had this, a little Toyota Echo that I drove until it completely died about 2 years ago. But what everybody is buying in the United States are these giant pickups. 70% of the car market now are all of these pickup trucks, which is a huge problem because, of course, they're more efficient. But they still have so much metal in them. And the problem with all of these things, like big cars, electric cars aren't really that different. People still park them on the sidewalks. They still clog the roads. And yet America is obsessed with the car, and it's going to smother us in CO2, whether it's electrical or not. The sufficient way to go, of course, would be to be like Stockholm in 1928, where everybody's on a bicycle. We have to look at everything we do and how we do it and pick the methods with the lowest requirement to run it and the lowest embodied energy. That's why I ride an e-bike, a Dutch e-bike, and never drive. And people say, oh, you can't do this in Canada, it's too cold. But you just dress properly and you're fine. And I do this, and I'm just fine in the coldest weather. Now, again, the problem is we've got this American dream, this North American dream of the big house and the big car towing the big boat. And that was the dream in 1960. And the only difference in the dream today is the house is bigger, the boat is bigger, and the car is way bigger. It's now a truck. Their houses, in the 50s, the dream was to get a house, and they weren't that big. They were lovely little things. And the dream now is sort of this Elon Musk all-electric house with solar shingles, solar power, a Powerwall battery in the wall, 2 Teslas in the garage. But it's big and it's expensive, and again, it takes so much to build it. Houses in the United States went from 983 square feet to 2,400 square feet, while the number of people in them went down from an average of 3.37 to 2.53, and the number of BTUs to heat it doubled. Sorry for all of the imperial measurements there. I'll give you some Portuguese numbers here about inflation and the cost of building going up and materials going through the roof, which is another reason why we have to reconsider how we build and how big we build. I was so impressed when I was last here with Marcio Calera's house, a great example of how you build simple and small and passive house. I keep looking at this plan. It's 107 square meters, and yet every North American house has to have 3 bedrooms and 2 baths and a powder room, and this even has what I love, which is a separate kitchen, all in barely 1,100 square feet, 107 square meters, half the area of a traditional house with everything you want in it. So, this was the slide I ended with when I presented last year, which was that, of course, every action matters, every bit of warming matters, every year matters, every choice matters, but I had added the line, upfront carbon matters. And now I want to talk about why this issue is so important for architecture. Architecture, yes, but for everything. So it's been called, most people have heard the term embedded or embodied carbon. And it used to be called embodied energy. And that made some sense because the energy went into making something. But when we started worrying about carbon instead of energy, embodied carbon made no sense because it's in the air. It's not embodied in the device. L. Ron Burrell, who's also spoken here, he and I had this debate, and we said, he called it, it's the carbon burp, the carbon vomit, the carbon spike. But it's emitted, so we have to find a better name. And I suggested, after some discussion, let's call it upfront carbon emissions. And this is a term that's caught on. This is a Canadian organization that is using it. And this is a British organization, the World Green Building Council, which wrote this paper a couple of years ago saying bringing carbon up front. And Carbon Up Front is the name of my next book coming out next year, where I'm discussing it. And what you're getting here is a preview of that book. So, upfront carbon, as I call it, they got more sophisticated about it, and they consider it one portion of the full embodied carbon. And you see all the stages here, that upfront carbon is the product stage, the raw materials, transport, manufacturing, and the construction. And nobody used to care about embodied carbon or embodied energy, as it's called here, because electricity was coming from coal. It was dirty and put out carbon. Buildings weren't that well insulated. And back in 1996, you can see in this drawing that basically the operating carbon overwhelms the initial embodied energy almost immediately in a couple of years. John Straub, one of the most best engineers, and about this wrote back in 2010 that the ongoing consumption of energy to operate, condition, and light a building is the largest single source of environmental damage. And basically that studies show that energy used in operation and maintenance dwarfs the so-called embodied energy of the materials, saying that 83 to 94% of the 50-year life cycle was operating. But a funny thing happens when you start making buildings more efficient. It takes longer and longer for the operating energy to overwhelm the embodied energy. You can see that line going down as buildings get more efficient. And then a Canadian builder and teacher named Christopher Magwood did a study looking at Ontario, Canada buildings that were built with foam, like we were doing a lot of spray urethane foam to put in our building. But spray urethane foam has a huge embodied carbon component from the propellants used to blow up the foam. And he found that a regular building built to the Ontario Building Code with very low levels of insulation compared to a foam building, because of the huge embodied carbon in the foam, it actually had higher carbon output over 30 years than the typical Ontario Building Code. And this was a shocker. It was like a light turning on, said one builder. We've been doing everything wrong. I mean, there's this hilarious passive house that was built, I think, about 7 years ago, where the thing was essentially solid foam. Now, foam at that time was made with propellants that were clear greenhouse gas problems. And here you've got a passive house built with solid foam. And everybody thought it was great because nobody was thinking about this issue of the upfront carbon, the greenhouse gases. Now people are. And this was a big study done by Architects for Climate Action in the UK that looks at what happens when codes start getting tightened. That right now a building, an office building, might be 55% of operating carbon and 45% embodied. But if you take the same thing in 10 years with the projected cleaning up of the grid to be more renewable energy, the electrification, and the better insulation, suddenly it's 95%. That they included replacement and maintenance and end of life and embodied carbon, but it still was bigger than the gray, the operational. And the grid is getting cleaner all the time. Forgive my terrible, terrible sketching here, but like I did my own graph looking at what happens as the grid gets cleaner. Like where I live, for instance, the grid is 94% clean, hydro, and nuclear, that basically it never gets above the upfront carbon. If you've got a heat pump system running on clean electricity, it's basically all embodied carbon, or as I call it, upfront carbon. And so I came up with, I called this upfront rule, ironclad rule of carbon, which is, as our buildings become more efficient and we decarbonize the electrical supply, emissions from upfront or embodied carbon will increasingly dominate and will approach 100% of emissions. So remember what this is saying, that your buildings are basically all embodied or upfront carbon. And it's not just them, it's also cars. When everybody thinks that they're going to buy all these electric vehicles and they build all these electric Fords, everybody forgets about the upfront carbon. There was this great poster which Hyundai put up. Why shouldn't a car have the same emissions as a bike? And the graffiti from someone who knows their energy said, because of the carbon embodied in the materials. When I did the math on this, I found that the Ford at the time was going to have a bigger carbon footprint, an electric pickup truck, than a small European gas car. And, everybody's sitting there now saying electric cars are so wonderful, we're going to invest in electric cars and that, but not when you start thinking about what it takes to build them. That basically the carbon footprint might be so high that basically it's off the scale compared to even a little gasoline car. Here it says 180,000 kilometers until it takes over. This was done by another group that came basically to the same conclusion, that these pickup trucks are just too big and that electrification doesn't solve the problem. I said this last year. I was just doing this when I was doing my book, that I have every Apple toy that Apple makes and that they all add up. And if you look at this from I showed this drawing last year. Look at my iPhone 11. It's got an 80 kilogram carbon footprint. But when you look down at the small print, you find they say that 83% of it is production and only 13% of it is the use. But that's based on the average American electrical supply, which is a lot of coal. So where I live in Ontario, in fact, that phone is not 83% production because there is no carbon from the use. So it's all 100% upfront carbon. And it's the same for my watch, which I obviously couldn't lift my wrist if it actually weighed 38 kilograms. And it's all embodied carbon. So what we have to do, as the British showed in that World Green Building Council, is that we can't just say we've built a really efficient passive house and we've done our job. We have to consider the upfront and embodied carbon emissions and reduce them at the outset. We have to question whether we need to use materials at all and consider alternative strategies for the desired function. We have to reduce and optimize, use low-carbon design guidance, and there is now that pH ribbon tool that you can use, apply design approaches that minimize the quantity of new material required, and prioritize materials that are low or zero carbon, and plan for the future for end of life. Or, as it is all put into a chart, the first thing we should do is build nothing and explore alternatives. Not very good if you're an architect. It helps that you want to build. Build less, make use of what we've got by renovating. Build clever by optimizing it. And obviously, build efficiently using low carbon and eliminate waste. And we have to think about the materials we build with and look at where the energy comes from. I mean, in cement, it's almost all coal. Iron and steel is almost all coal. Aluminum is almost all electricity. And this is chemistry. This is a real problem because the way you make steel is you throw carbon into the iron oxide, which is the hematite, and basically the carbon reacts with the oxygen and you're left with steel and carbon dioxide. There's new technology that they can use hydrogen instead of carbon, and they got water instead of CO2, but to decarbonize the whole global steel industry would require 600 gigawatts, 52 million tons of green hydrogen, which is doesn't possibly exist. It's the same with cement. It is a chemistry problem in it that basically to turn the limestone into cement, you basically have carbon dioxide as the byproduct. 50% of its footprint comes from the chemical reaction. Aluminum, everybody loves the idea of aluminum because it's totally recyclable. But 26% of aluminum goes into construction and 26% goes into these stupid pickup trucks. And everybody thinks it's all so green and wonderful. This building was on Dezeen last week, entirely made out of aluminum. Isn't this great because it's recyclable? But there isn't enough. The use of aluminum grows all the time. It doesn't all get picked up. A lot goes to the dump. So we have to start thinking about what we do. And again, this is the same thing. It's chemistry. Aluminum oxide, alumina, you put a lot of electricity into it, and that breaks the bond, which releases the oxygen from the aluminum. But where does the oxygen go? It combines with carbon and comes off as carbon dioxide. Now, these guys, Justin Trudeau, took some money from Tim Cook of Apple, and everybody's investing in this Elysis aluminum, which uses a different kind of anode so that it isn't a carbon dioxide reaction. And this is being done also in Russia, the biggest source of green aluminum is Russia. And guess what? The war is coming in and messing that up completely, as they're talking about banning Russian aluminum, which is the greenest aluminum we have. And even green aluminum is a huge problem because of bauxite mining. It's destructive and terrible, and it leaves behind these lakes of red mud after they take out the aluminum. So what do? Well, there's the issue if we can start using more wood. But we know that's problematic from the forests that we have. How much wood can we actually get? How fast does it grow back? And, we're still building stupid buildings, even with wood, because people like looking up and seeing the wood. And as Monty Paulson, Passive House expert, says, glass boxes are horrible buildings. Glass boxes and wood frames are still horrible buildings. Wood frame buildings on massive, massive parking garages, on these carbon icebergs below our buildings, are horrible buildings. And people just don't really get this whole picture. Here's a thing that I was pitched on from Valcuccini Kitchens. They put one into the wonderful Stefano Boeri buildings, which everybody uses as their poster child for the greenest buildings in the world. And Valcuccini is saying they're the greenest kitchens. So here, why green building may be affordable. They even show this for this when they're some of the most expensive housing in the world, these buildings. And the concrete footprint to hold up those trees, the upfront carbon that goes into making this building, it'll take decades for those trees to suck that up. And the Valcuccini kitchen is made of glass. So when you think of these things in terms of upfront carbon, when you've got a glass kitchen instead of, say, a wood kitchen in a building that's got like 50% more carbon than it otherwise had, none of this is green and none of this is sustainable. We have to rethink the way we think about this. We have to rethink our choice of materials. I always show this building as the greenest building, where it's even made of thatch, Archetype's Enterprise Centre, but it's in the UK, where they have a tradition of building with thatch and wood and materials like this, natural materials, a palette of materials like that. You don't have that in Portugal, but you do have stone. And according to engineer Steve Webb, making stone has half the carbon footprint of concrete, and stone is can be 2.5 times stronger. This is a building in London that was built of stone. A tree takes 25 years to grow 1.5 cubic meters of material. If we quarry the stone under the tree, we can get 500 cubic meters of stone in a month. After the Second World War, France's government turned to stone because they didn't have materials like steel and concrete and coal. So they figured out better ways to quarry and built all over the south of France and in Algeria. This is Fernand Poulon building these buildings in Marseille. I didn't even know they were stone when I took a picture of them because I just liked the building. And they're still doing this. They're still doing this in France. This is a new social housing project that looks fantastic. In Portugal, you've got a great history of stone. You've got lots of it, and boy, do you know how to use it. And, in old buildings and new buildings, you've done it so well. And, of course, you have my favorite insulation, which is cork. And you can do all kinds of wonderful things with cork. So here we are again at the SER framework. And I think this is the thing that we will end with. We've got to, of course, efficiency. You build passive house as the minimum energy standard. Then we've got to go for also improving the energy, the upfront carbon, so we have to measure and minimize it. We have to obviously build with renewable materials and use renewable power. And by the way, stone is renewable. We're making more of it all the time. It takes millions of years, but that's what happens with plate tectonics. Very slow, but renewable. And we have to think about what we build on the sufficiency side. Build nothing, build less, and build simple. Thank you very much.